first 5, the first one gets a 100 and then just goes down by 2 points.
No, that's too many A's.
It goes by 10 points.
So people are getting like a negative 120 on the final?
Yep.
And if you get down to negatives, you change it to a positive. So you do either.
Something like that. All right. So if we want to do weak acid equilibrium problems, so we probably should have our notes out and a pen and pencil ready. There's a couple problems we're going to work today that are going to require, I think, more space to think appropriately, more space than you are given. So you may want some notebook paper. So we'll have a quiz testing something about something next class. Yeah. Likely subject will be chemistry, but I don't promise that.
It's actually a quiz over the history of SpongeBob.
They have back on SpongeBob's backyard.
No, you know what? It's a
Okay.
It's a quiz on Bill Nye's life. Like you have to know his entire biography.
Yeah, he's an actor who got a job, and now he plays somebody who knows science. We can all read scripts. So list the major species. You're going to figure out who's actually making the hydrogen ions. We're going to use values of equilibrium constants and figure out who's going to dominate in producing the hydrogen ions. Then we're going to write the equilibrium expression for the dominant one, because we don't really care about the one that's just contributing a little bit. Y'all remember this from the last class. We talked about, for instance, that very weak hydrochloric acid didn't change the pH because there's so little of it compared to the naturally occurring autoionization of water, right? So the pH didn't change. If we had, 1 times 10 to the minus 10th hydrochloric acid, the pH is still going to be 7. Okay? All right. We're going to define the changes, set up X, set up our rice tables, just like we've been doing. Okay? We're going to substitute equilibrium expressions in. For weak acids, this is an assumption we get to automatically make so that we can avoid using this quadratic. We're just going to practice avoiding the quadratic. It was cute. It was good. We know you actually have a real use for it. It wasn't just some fun thing that you learned in algebra. We're going to assume that X is going to be really, really small. So whatever this number is, subtracting this very, very small number from it's not going to change anything. And so we're going to say this is chemistry. We're going to practice some gray math. We're going to say that's close enough. Okay? We're then going to calculate the hydrogen ion concentration and the pH. Let's consider 2 aqueous solutions. HA and, well, I'm not going to talk about H. I don't want to talk about HB. We're going to come back to that one. Let's look at hypochlorite. Okay? And it does all this fun stuff. We don't care. This is what we care about. It also forms a weakly acidic hypochlorous acid. Hypochlorous acid is a Ka of 3.5 times 10 to the minus 8. That is weak. Calculate the pH of a 0.1 molar aqueous solution of hypochlorous acid. So let's set it up. First of all, yeah. Is there a question? Oh, okay. First of all, who is going to be contributing the most number of hydrogen ions in this situation? I've got water. Water's got a Kw of 10 to the what? 14. Negative 14 compared to 10 to the minus 8th. So who's going to be contributing more? Hypochlorous acid. So we're going to assume that's going to be the dominant. Okay. Oh yeah, we need to list the major species. So major species in this case. When I take this stuff and I drop it in water, what are the species that are going to be by far in greatest concentration? So from the water, I want to write this. So from the water, H2O is going to break into. Is there going to be a lot of this? Is there going to be a lot of this stuff? No, because the Kw is what again? Okay, that tells me this reaction is mostly on what side? It's mostly the reactant. All right, let's look at our hypochlorous acid. Okay. What's its Ka?
3.9 times 10.
And which side of the equation is that going to be on? Still favors the reactants. So my two major players in a solution of hypochlorous acid, in a 0.1 molar solution of hypochlorous acid, is water and the hypochlorous acid itself. Make sense? So my next question is, out of those two, which one is going to dominate in production of hydrogen ions? That's where I was headed with a few minutes ago. The hypochlorous acid. Because this is 10 to the minus 8th, even though both reactions favor reactants, this is still going to be where the hydrogen ions are coming from. They're coming from the hypochlorous acid. Everybody good? All right. And there it is. Okay. So we list the major species. We just did that. Both of these can produce hydrogen ions. However, we know that the hypochlorous acid is going to be producing most of them. So I'm going to use this equilibrium expression. Now, when we were doing salts, we didn't list anything on the bottom. Why was that? Solids. Why do we list that on the bottom? Because it's aqueous. Very important to make sure you guys understand that. This one actually has a bottom number. Good? All right. What do I know here? I don't need a rice table for this one. If I was doing this, I wouldn't necessarily make a rice table because I'm going to go ahead and assume that the x that's going to be subtracted from the bottom is very small. So what value should I put here? The 0.1 molar, the initial concentration goes right here. That's not my equilibrium concentration. I realize that. But mathematically speaking, however much I remove from that initial concentration isn't going to change my number very much. So that's what I'm just going to put the initial concentration down here. That leaves me with these guys. These are the same, right? So if I say x here, this can also be x. And so Ka 3.5 times 10 to the minus 8th x squared over 0.1. And from there, I can solve. Let's see. Just like we did before. All the math is the stuff we've been doing for the past couple weeks, all the same. This math is all the same. We're just moving it now to talk about acids and bases instead of talking about salts. So see if y'all can go ahead and solve that for me. Did you get it? All right. Good? You guys good? You see how easy this is? You just got to think in terms of acids and bases. We're not going to worry about validating this stuff. I don't ask you to do that. Just assume it's 5%, yeah. But I am going to ask you, so since we know the hydrogen ion concentration, you should be able to calculate the pH. Can you do that? You got the pH?
Yeah.
Okay, make it happen. Did you get the pH? Good, of course you did.
Don't get that confident in me. Oh my God, congratulations.
Did the person behind you finish watching the TV show?
Emma? I don't know.
Yep. Y'all okay with that? Let's see. Okay. All right. What are the major species present? Oh, we're not going to worry about that because it's not necessary. All right. Let's have some fun now. Now let's introduce common ion effect with acids and bases. Actually, just acids in this case. So I've got two different acids. I've got hydrocyanic acid and what do I call this other one? Nitrous acid, right? Nitric would be the nitrate with a 3. So nitrous acid. So I've got 1.0 molar hydrocyanic acid and 5 molar nitrous acid.
Why is that hydrocyanic acid?
Because that's what you call it.
Even though it's a...
It's not an oxyanion. Yeah, I know we were a little confusing with y'all. I try to keep that clear as I teach now, but I know 2 years ago we were still not. We were saying polyatomic, right? Yeah. It's just for oxyanions. All those 8s and 8s and stuff like that. Yeah. All right. So after we're doing this, y'all can probably figure this part out. We're then going to take the common ion effect and figure out how many cyanide ions we have. Because y'all could figure that out real easy if it was just cyanide or hydrocyanic acid in there, right? But now we're going to mix a different acid in and see what happens. All right. So first things first. Like this is the one where you're going to want a separate piece of paper. I don't feel like they've given you enough room in that box. Because you got to do several different things at once. Well, not at once. You can do them in stepwise, but yeah. All right. We good? Everybody ready? You got some paper? All right. Good? All right, here we go. They're both weak acids. They're both going to be largely undissociated. So my big contributors are going to be the hydrocyanic acid, the nitrous acid, and the water. Okay? All three of these guys can contribute hydrogen ions. Who's going to be my big contributor? I'm going to push it back to here.
Nitrous acid.
Who's going to contribute the vast majority of the hydrogen ions? Nitrous acid's definitely going to contribute the most. It's got a Ka of 10 to the minus 4 compared to water's 10 to the minus 14th compared to hydrocyanic's 10 to the minus 10th. Okay? Y'all good? You see what we're doing here? These are my reactions. So I can get rid of 2 of these, and I'm just going to consider the nitrous acid. Because whatever contributions these other guys are going to be so small, I can just ignore them. I can just ignore them. So we could do this all at once. This might get a little complicated, as it says, so we're not going to. Because we like easy stuff. This is why we're in AP Chemistry. We like easy stuff. Okay? So we're just going to assume that's going to take care of it. We're going to write our little rice table if we want to. We're going to write our equilibrium expression. We're going to assume that however much X leaves is going to be so minor that we don't care. So I want you guys to solve, based on this, solve for the hydrogen ion concentration first. Let's take care of that. Everybody got an answer for me? We did a little ice table. So we should have gotten that the hydrogen ion concentration is 4.5 times 10 to the minus 2. Did we all get that?
Yes.
Fantastic. You guys are going to do really well. Now, that step's done. Now we're going to move to the next step. And the next step is to figure out, well, how much cyanide is there? How much of the cyanide ion? If you remember, the reason I care is because I've got HCN. And that's going to be H plus CN minus. What happens to my concentration, though, if I increase this? If I increase H plus, what happens to the equilibrium? It's going to shift this way. And if it shifts this way, what happens to this? This is going to go down. Now, I recognize we're not at equilibrium, but I still think it's helpful to think about it, because that's what Le Chatelier, I want to be super clear, Le Chatelier's principle starts at equilibrium, and then you perturb the system. I still think it's reasonably helpful to think about it from this perspective, because we could have started with a nice, pretty solution of hydrocyanic acid and then added it, and you'd still end up with the same results. So again, it's a way to think about it. All right, so that's what's going on here. This is what I'm getting ready to ask you to solve for, is to tell me how much cyanide ion are present with a common ion effect. So let's take a look here. Oh yeah, we'll calculate the pH. 1.35. We'll come back to that in a second. All right, the only place cyanide ions are coming from is the hydrocyanic acid. Good? Okay. There's my equilibrium expression, right? Normally, we would put my original concentration of hydrocyanic acid in there. Everybody okay? The difference is, in this case, we have a hydrogen ion concentration. You're going to take the value that we just calculated and plug it in here, the original concentration of the hydrocyanic acid there, or prussic acid, or you can just call it hydrogen cyanide, but that's okay. And then you're going to solve for Cn. There we go. That's what you're doing. And what do we get? Very good. So y'all can solve these problems easily. Everybody okay? All right, let's keep going. Everybody okay with that? So you guys know how to handle Ka. It works just like the KSP you've been dealing with, the Kc, the Kp, all the math stays the same. I do need you to keep in mind, you got to include aqueous and gases, but not liquids and solids, so keep that going. All right. Percent dissociation, the amount dissociated over the initial. So as the hydrogen ion decreases, as this concentration decreases. However, the percent dissociation increases as this decreases. Can y'all chew on that for a second? Sometimes students have a little trouble chewing on that. Right. The amount of hydrogen ion decreases when I decrease this amount. The percent dissociation increases as I decrease that amount. This amount goes where in this equation? The bottom. So I make that go down. What happens to this number? This number goes up. Yeah, you can think about it in math. You can think about it what's going on in the water. Doesn't matter. Either way, as long as you get that stuck in your brain. All right, let's calculate the percent dissociation of acetic acid in 1 molar acetic acid. we're going to go through this whole process. Hopefully everybody got to this point in the formula. That's a cool pencil. Good. Got it written down. All right, here we go. Rice table if you need one. I don't do one for these more simple ones. I will do one for the ones that are a little more complicated, but there's your equation. Everybody get to this point? X is 4.2 times 10 to the minus third. I then take that number, divide by 1. So my percent dissociation is 0.42% dissociated. Percent. Got it? Everybody good? We good here? Good there? Okay. Use Le Chatelier's principle to explain why percent dissociation increases as the concentration of the weak acid decreases. Okay, I want y'all to actually think about this. That's exactly it. Yep. We're going to shift it to the side with the greater particles as the percent dissociation increases. Good. Excellent. Lactic acid, chemical that accumulates in the muscle tissue during exertion. A 0.1 molar aqueous solution, lactic acid is 3.7% dissociated. All we're doing is going backwards. There's a lot of text I'm going to click through here. You guys know how to take that same equation we just did and run it backwards, right? Y'all write that down and go backwards, and then I'll run through the clicky. I think I got like 6 slides here to explain that. Did y'all solve it? So we went through all that. Just run the reaction, run the equation backwards. So X is 3.7 times 10 to the minus third. X in this case, based on that acid, is also the hydrogen ion concentration. Yes. So that makes my life super easy. If I know that, I also know the pH. Okay. And if I know that, I can use this to calculate the Ka, right? Because this is the concentration of that, and this is my initial concentration. So we'll plug that in. We good? All right. Are you good?
I understand everything right
You actually look like you understand.
now. Yeah, I don't have an existential crisis.
From like a health perspective, lactic acid builds up in
Yes.
and then dissolves back in your bloodstream.
Yep.
So it's basically a Le Chatelier's. The dissolved parts are getting drawn out, so it keeps going.
Yeah, if you'll do it, we talked about it last class, you'll do a cool down exercise. This is what a lot of people don't do. Like if you're running, just walk a couple laps and it'll help, and then of course stay hydrated and stuff, right?
If you don't do a cool down, that's part of why you get so much of that
Like a lactic acid doesn't get pushed out of your. If you're doing a cool down, your blood's still moving, and it pulls it off of you.
It'll circulate it out, but if you don't, it'll sit there.
And then it's an acid, so it doesn't feel comfortable.
Did you know Aaron Connolly?
Uh huh.
You do know Aaron Connolly?
Oh yeah.
He, what did he do to himself? He went to like a spin class, and there was so much lactic acid buildup that his kidneys failed.
No. A spin class?
Yeah.
Like,
Like
oh,
Stationary
cycling.
It's called a spin
spin.
class.
No, they spun around like ballerinas for an hour.
That's what I thought.
That's what this class is, right?
It's like CrossFit, but circle fit.
Circle fit.
Like a Peloton?
No, they just ride stationary cycles,
It's wiggle fitness.
wiggle things.
All
right.
Telling us about lactic.
So now let's talk about acid-base problems. So again, there's a nice stepwise thing to think about. We want to think about the major species. I want to look for the reactions that can be assumed to go to completion. Once we figure they can be assumed to go to completion, we'll figure out the concentration of the products, write down the major species, look at each of the components and figure out if it's an acid or a base. Use the equilibrium that will control the pH. Write that equilibrium down. We're going to compute initial concentrations. We'll figure out X. Okay? We'll check the validity of approximations. We really won't. We'll calculate the pH and other concentrations as required. We missed something. Why do we? No, it didn't. Okay. It's just me again. All right. So I have a 0.15 molar solution of weak acid is dissociated, 3% dissociated. From there, you should be able to calculate Ka. So calculate Ka, and if you did that, you would find that it's 1.4 times 10 to the minus 4th. Pause this video now. No, I'm just kidding. Too late. The Ka for hydrogen fluoride or hydrofluoric acid is 7.2 times 10 to the minus 4th. What are the major species in this case? So write down the major species in this case. Good? Y'all got it? What do we got? Okay. Water is a weak acid or strong acid? Weak acid. Really, like really weak, right? Because Kw is 10 to the minus 14th. What do we know about hydrogen fluoride, hydrofluoric acid? Also very weak. Look at that, minus 4. Very weak. So who's going to be the major species? It could be HF and H2O. Right? We're not going to see much dissociation from that HF because it's weak, so it's going to stay on the left. We're not going to see dissociation from water, so it's going to stay on the left. So the two major species are hydrofluoric acid and water. All right. Which of the following best represents the plot of hydrogen ions versus the acids? Any kind of generic acid there. Weak acid, right? Which plot's going to, I mean, you should be able to eliminate some of them, but all right, does A make sense? No. Does D make sense? No. Does E make sense? To a point. Then what?
Well, then it'll stop increasing.
Uh-huh.
And it'll be B.
So it should be B, right?
It's
Yeah.
like at one point it'll hit
Yeah, it'll.
one round.
Okay. All right, cool. The percent, these are fun ones now. The percent ionization for a 4 molar weak acid is what than the weak acid of 8 molar weak acid? That's what it is. The percent ionization of a 4 molar weak acid is what the percent ionization of an 8 molar weak acid? It is greater than. That's correct. Okay? You remember that. Bottom number's smaller. Yeah, okay, cool. How about this one? The pH of a 4 molar weak acid is what the pH of an 8 molar weak acid?
Oh, greater.
This is where you got to keep your thinking caps on. All right. Who's going to contribute more hydrogen ions? The 8 molar is going to contribute more hydrogen ions. Do we agree on that? Does that make sense from everybody? I'm going to have more hydrogen ions. Okay. If I have more hydrogen ions, my pH is going to be what? Smaller. So the one that has the fewer pH is going to be greater. Yeah, we've got to, that's got to get to be automatic, right? pH goes down, that's hydrogen ions going up. All right, so yeah, it's greater than. All right, now let's talk about strong bases. The beautiful thing about this is it's going to work just like acids. The only thing that's going to change is instead of doing Ka, it's going to be Kb, which is just like we did with Ksp, which is Kp and Kc. You just got to remember what you're talking about. All the mass stays the same. You just have to think about it a little differently because it's bases. And so remember, bases in the Bronsted-Lowry, bases are proton acceptors. Oftentimes, and generally speaking, we're going to talk about things that have hydroxides in them, but that's not required. All that's required is that it can accept a hydrogen ion. All right, so strong bases, hydroxides of group 1A elements and alkaline earth hydroxides. Okay, let me be clear, we consider 8 strong bases. Look at your periodic table, start with lithium. Go lithium, sodium, potassium, rubidium, cesium, over barium, strontium, calcium. I and others don't consider magnesium hydroxide to be a strong base. The attraction's too strong. Okay? I think he does. Zumdahl does. Just be aware of that. I don't think you're going to see a lot of it. Calcium hydroxide's another one of these anomalies that we're actually going to mention here in a second. It has low solubility, but it's a strong base. That is, water particles, when you're in the lattice structure, water particles can have a hard time getting it out, but as soon as it does, it will fall apart. Okay, so you may see calcium hydroxide, if I have to make that for the lab, takes forever because I basically got to keep a stir. I usually set it on a stir rod and let it stir and go off and do something else while carefully watching it.
Take the safety quiz.
But yeah, so because it just takes a while to get in there, and the magnesium hydroxide can do that as well. But just be aware of that. And they're really easy to remember. All right, here we go. It possesses low solubility. All right, I don't really care about the rest of this. Let's talk about this. Let's do the pH of 5.0 times 10 to the minus 2 molar sodium hydroxide. All right, so there's a couple of ways to attack this problem, and there's one way that I teach in honors that I think is easier, and that is, this is what kind of a base? Strong base. That means if I take NaOH, okay, I'm going to actually assume that whatever the molarity of this is also the molarity of the hydrogen, of the hydroxide ion. Okay? Simple way to handle this is to take the POH of this. POH of that would equal what? 1.3. Y'all good with that? Therefore, the pH is equal to 14 minus 1.3, which is, what is it? 12.7. Let's put that on the side here and see if that works out. Okay. Everybody good with that? Yeah. Question? Okay. So this is the way I would recommend. The problem is it does require you to think a little bit in terms of POH, and some people get confused. Same rules apply. Anyway, I wrote that up the side here, so we'll take a look and see if that works. All right. Here's our major species. This is a strong base, so that my major species are sodium, hydroxide, and the water. Again, as we point out, water is a weak acid. It's also a weak base with a Kw of 10 to the minus 14. In this situation, it's not going to be contributing any significant amounts of hydroxide. Okay. So there's my solution. This is what they're suggesting, that we go with the Kw method. Why in the world would you do this? Okay. So they want you to understand this is what's going on, that I've got a Kw of 10 to the minus 14. And so you can do all this punchy and all this stuff, and you come up with this, and then you come up with 12.7. If you needed to know the hydrogen ion concentration, you could do that, right? That is 10 to the negative 12.7, right? Which should get you this number or something very, very close to it. Yeah. Okay. All right. So, as an estimation, when you're estimating pH, like on the multiple choice portion, something you should be aware of is if this number is not 1, you can look at that number. This number is going to be 1 digit lower than whatever that is. See, that's 12 and that's 13. If that's not 1, you always know that first number is going to be 1 lower than that. Y'all follow me on that? It's just a quick cut. It will usually let you eliminate at least 2 of your answer choices. But I've actually seen several questions where just knowing that, it's only one possible answer. You don't have to do the math. I've watched kids, I don't know if it's on this test that's coming up, probably not because I'm going to have to write it. I've watched kids and I've seen on the notes this long drawn out, they're trying to do math. And I'm like, if you know this, if you really get logarithm, you don't need to do math. You just look and say, hey, that's the only possible answer because these two are the only ones that match up like that. All right. Cool. So, what's happened here to the hydrogen ion concentration? Why did it get reduced? Well, I've added a bunch of hydroxide. I've increased the hydroxide, which drives the reaction what direction? It drives the reaction to the reactant. And when that happens, what happens to this? It decreases. That's why you have this relationship that Kw is 10 to the minus 14th has to do with these two concentrations. Okay? Make sense? All right. So again, Le Chatelier's principle comes back into play. All right. When bases react with water, they're going to increase the concentration of the hydroxide ion. They do that by decreasing the what? All right, I'm going to draw the autoionization of water again. So I want to talk about this. Okay. Assume all the little aqueous symbols are there, whatever else you need. Y'all good with me? All right. If I add something to this that is a proton acceptor, what's that going to do to this? It's going to decrease this. If I decrease this, what direction is that going to shift the equilibrium? It's going to shift it towards the right. If I shift it towards the right, what's going to happen to the hydroxide? It's going to increase. That's how things like this, well, let's stick with something simple, ammonia, which is NH3, right, can become NH4. Should probably put a little H plus here. Okay? It's going to become NH4 plus. It doesn't have a hydroxide, but it still increases the hydroxide concentration by accepting that proton, by taking that proton, shifting the equilibrium this way. Does that make sense? We good there? All right, cool. I want to make sure that everybody's on board with how that works. Let's see, where did it go? There it is. All right, general reaction and its equilibrium constant, Kb. Kb, same thing, okay? So the Kb is my base plus my water is my conjugate acid and the conjugate base, which is your hydroxide. This is what we typically care about. So you're going to write it just like that. The Kb is the reaction of the base with the water to form the conjugate acid and hydroxide ions. For weak bases, Kb is small. This should be, like, we all know this by now, right? Okay. Let's calculate the pH of a 1.0 molar solution of methylamine, which has a Kb of 4.38 times 10 to the minus 4th. Same as before. Same math. What's that? Huh. I thought about it last time, but I didn't. I can look it up here. I'll draw it. Somebody's probably curious. Somebody at home is probably curious, so I will draw it. And I'll probably get, you know, yeah, that makes sense. Right? NH2, yeah. There's methylamine. For those of you who are curious, now I'll probably get a visit from cybersecurity for looking it up. Good. So that guy can accept a hydrogen ion. You got the KB written, right? All right, here we go. It is weak. That means my major species are the methylamine and the water. Both are bases. However, looking at our numbers, 10 to the minus 4 is much larger than 10 to the minus 14th. All right, so we're going to suggest that this is what's going on. This is picking up an extra hydrogen ion, leaving us with excess hydroxides. Punchy all that in there. I got one of these for every one of those. We're going to substitute the little letter X for that, right? That number on the bottom makes my life super easy. What'd y'all get? Did you get it yet? You have an answer?
That should be pOH, but no, this is the pH.
Okay.
pOH was like 1.7.
Seems reasonable. Wasn't it 1? So you can put a rice table together if you need one for this particular. I tend to think these are simple enough, but anyway, let's plug this all in there. Okay, and is that what everybody got? So you can see they've started doing the same shortcut we do. So the pH of 12.32, this is a what kind of solution? Acidic or basic? Basic. This is definitely a basic solution. Okay. Y'all see how the KB works? Just like the Ka and everything else. Super easy, super straightforward. What's that? Yeah, all the math's the same. So at least y'all will do well on that part of the exam. Okay, except that we had a FRQ that had multiple of those that people didn't. Yeah, not so much fun, right? Okay, let's consider two separate solutions of equal concentrations. I want you guys to actually think about this and make a guess. Make the correct guess. It might help to write formulas. It might help to write equilibrium equations. Someone sent an email suggesting I might want to give a mean test.
A what?
A mean test.
Who said that?
Another person.
A student or another teacher?
Teacher.
Oh, okay. For
It's like something to
pre-AP?
Jay Fox would say.
He goes, here's a test in case you want to give them a mean one. And I said, well, of course. But of course. All right. Sodium hydroxide's formula is what? Barium hydroxide's formula is? Except it's really going to be that. We're just going to assume. All right. So for the same concentration, I'm going to have twice as many hydroxide ions, right? Easy. All right. Which one of these has the lower pH? What does?
Sodium hydroxide.
Why does sodium hydroxide have the lower pH?
Well, I can tell you what barium doesn't.
Why does barium doesn't?
So, because it has twice as many hydroxides, it's going to push the equation back towards water. So the hydrogen ion concentration is lower.
Right. Do y'all get that? This is one of these multi-step, like at first you'd be, oh, well, there's twice as many hydroxides. So that means the pOH would be higher in the barium. If the pOH is higher, the pH must be
Less.
so it's got, so the sodium hydroxide has a lower pH, right? Okay. Good? Yes. I have to have less hydroxides to have a lower pH. Since I have more hydroxides with barium, I have a higher pH. Yeah.
Wait, say it like that?
No.
Oh.
This is awful.
Yeah, run that through your brain about 3 or 4 times.
I was fine when you were like,
Let it ferment.
It goes up, it goes towards the reactants. And then you said higher OH, or higher hydroxide means lower pH. And that's when I started getting.
No, it actually means higher pH, but yes.
You know that TikTok where it's like
Higher hydroxide is higher pH.
No,
Higher hydroxide is higher pH.
larger concentration of hydroxide
wouldn't that mean it
would
has a
mean
higher
a
pH?
greater TOH.
Why? Freaking pH.
Because high pH means basic.
Yeah, oh wait.
So
Yeah.
a higher
Oh,
pH.
okay.
Sorry.
No, this is a big deal. You are not alone. Best students all over the planet struggle with this. This is what you have to, Actually, this part is what I keep in my brain. I try to hold my eyes over the OH stuff. Really, like I do, like I convert quickly to pH before I try to think about it. Like I don't even, we used to teach a pOH scale, and I just quit. I'm like, pH scale, I just want you to think in terms of pH. Get it to hydrogen ions, think in terms of pH, and don't think about pOH.
So the more hydrogen ions, the lower the pH.
Right. And you can think about your stomach acid is 2, right?
Yeah.
And your Gatorade is 2.5.
It has a lot of hydrogen ions.
Has lots of hydrogen ions floating about. All right.
Why do we use this garbage scale?
Because some old white man said so.
Don't pick one scale, pH or pOH. You don't get both.
Right.
Why don't we use either? Why don't we use like some linear scale?
Well, you know, somebody thought that having things on a log graph, y'all don't. That's one thing y'all missed is actually plotting things out on log graph paper. Have y'all ever actually even seen log graph paper?
I didn't know that
You should ask Mr. Fox next time you're in there. He probably has some laying around, some log graph paper. I mean, he's younger than me, but he actually, since he does math, that's, you know.
He ruminates about it. He's like, you ever heard of a lithograph?
Ask him about a slide rule.
Yeah, he's talked about those.
Yeah.
He's talked about cylindrical slide rules.
Slide rules are actually, my father-in-law used to have one. He showed me how it worked, and I was like, that's actually pretty impressive for what you could do with it. I mean, anyway, let's go back here. What volume of water must be added to 100 milliliters of an aqueous? Don't yell it out loud. I know a lot of y'all know it immediately. Go ahead and solve this. Think about what the scale that we just talked about is. Mm-hmm. Anybody got it?
Yeah.
Okay, what scale are we doing again with P's? H? The P is a
It's
log scale. So if I want to go from 12 to 11, I need an order of magnitude higher. So my volume needs to go from 100 to 1,000.
See, we
Hi.
did logs in quarantine last year.
Some of y'all did. Most of y'all didn't.
Yeah,
Okay, so what's the answer? Everybody got B, right? Because the question says how much to add. We have a question similar to this that the babies struggle with every year except for last year because most of them didn't do anything. And it says add because we're doing solutions and acids and bases and stuff. And so there's a question that we always ask, and the question is how much do you add to get to this? And they miss it year after year after year because they didn't read the word add. Not what the new volume is, how much do you need to add? Okay, good. Y'all got it? Need to add 900 mils to end up with a final of 1,000. That would change my pH from 12 to 11. Cool. Polyprotic acids. No.
Are we done?
Yeah.